So it'll be the same drill as usual. Today's recitation will be optional and open to all. It will be a study session for the exam, so you can work problems, do any of the studying that you want in groups. Key will be there to help you study, and then anyone can go to that, or it's optional. He will have a bunch of homework to turn back to you. If you just want to go at the beginning and get your homework and leave, that's fine. So he's gonna. I thought he would have them for me or lecture for me to turn back to, but he said we'll have those in recitation. So you can just go and get your homework and leave, or you don't have to go at all and you get your homework later, or you can go and get your homework and stay and study. It's optional. And then Thursday we'll do the exam. We'll have class for about 45 to an hour, somewhere in there. We'll start the exam about 10 o'clock. Okay? Any questions about that? Oh, and then I'll have extra office hours tomorrow. Let's try, I was going to say do late morning. Can we do 11 to 1? Does that help? So I'll do those who are asking me about a Wednesday office hour, will you be able to make 11 to 1? Ezra's good. Good. Okay, so we'll do 11 a.m. to 1 p.m. I'll do an extra office hour. I'll have my regular office hours today from 3:15 to 4:45-ish. And then, so that'll be it. So that you have this afternoon and tomorrow morning. And then you can feel free to email me any questions that you have along the way. And then whatever keys office hours, take advantage of those as well. But study hard and then come have conversations with me. This is how you're going to do the best on the exam. Study hard, figure out what you're not getting so well, and then get in and ask questions. And it's in a conversation with me that we will flush out what you don't, your deficiencies, and get those straightened out, okay? All right. So this one, our vector field is negative xy and y squared. And then they want, this is find the parametric vector equation. So that's the path, right? So here's the description of the path along y equals x squared from 0, 0 to 416. And so these types of functions are the easiest to parameterize, because all we have to do is what? Yeah, so when you've got like polynomials like this, the technique is t, comma, and then if x is t, then y is. And then we also have segments, and we have line segments, which we should know how to parameterize, and then circles, right? Circles, kind of the three major categories of these paths that we have to parameterize, and then all kind of have a different way of doing it. But these are kind of the easiest, t and t squared. All right, now we want the line integral of f along that parabola from the origin to 416. So let's actually, let's graph this vector field and then predict kind of what we can make a prediction for what the line integral will be. So what was it again? Negative y, xy, and y. All right, so let's take a look at this. And we want to go from, so I'm going to zoom out here on the, unfortunately, okay, I think that's good enough. So we're going to go, and then we're going to go along y equals x squared. to 4, 16. So from 0, 0, from the origin, work. It's on the other window. To 4, 16. All right, so what are these vectors doing here? So this is really, it's really kind of relatively small, but it's looking like get a better view of this. Okay, so this is, I think what this is a very small vector pointing almost to the left like that, but really small. This one also really small, but up a little bit more. A little bit more up, a little bit more up. So what do we think about this? What do we think about the value of this? What do we think about the value of this line integral based on these vectors? So really tiny, kind of to the left there. What would we guess about this line integral? What would you think? Okay. Yeah, so we got maybe some, what about the beginning down here? Just really super tiny negative. Then what about through here? Yeah, I mean it's not, they're not exactly orthogonal, but you know it's going to be, it's not going to, there's not going to be any major positive or negative contribution. What about right here at the end? Slightly positive. So this is going to be, we would expect close to 0, right? We got a little teeny bit of negative at the beginning and a little teeny bit of positive contribution at the end. Does everyone see how we're getting that? Does that make sense? Right, you're going to take what? You take the component of all these vectors along the way in the direction of the curve. So you got your components pointing back against the grain here, and then you're kind of going perpendicular to the grain, and then a little bit with it. So maybe that the whole thing will be close to 0 here. So let's set it up and see. So we want to do integral, and since we know x goes from 0 to 4, so this is easy, 0 to 4. And then we're going to have negative x y is, I mean, negative t times t squared, so negative t cubed, and what, t to the 4th. So there's the vector field rewritten in terms of our path, right? Because all along the path, this is true, right? X equals t and y equals t squared along the path, and that's all we care about is along the path. So we can make x equals t and y equals t squared. All right, and then dot dr, right? Dr, so that's going to be 1 and 2t, and then dt. And we're going to go, t goes from 0 to 4, because that's, t is the same as x in this case. All right, so let's see how this works out here. So we got negative t cubed plus 2t to the 5th. Did I do the math right? So negative t to the 4th over 4 plus 2/5, 2/6 t to the 6th from 0 to 4. Is my math right? Okay, so what is that? That's plug 4 in, you're going to get negative t cubed, negative 4 cubed, so is that negative 64? And I don't know what t to the 6th is. so 1/3 plus 1/3, 4 to the 6th. I see. I think that, yeah, it's going to be a little bit positive probably. What is that? Quite a bit positive. Plus 4 to the 6th divided by 3. Okay, so 1301. Let's make sure that's right, first of all. Negative 64. Remember in web work, you can always put just formulas in, right? So 1/3 times our expressions. You don't have to let it be your calculator. Okay. Got it right? So why the big positive value? Well, the picture, that one, where is it? That's this one. Yeah, so this is just to give you a feel for, so this rendering of the vector field is just giving you kind of a general idea of the relative magnitudes of the vectors. But like at 416, what is the actual vector at, say, 416? So the actual vector at 416 is what? Negative 64. Yeah, so it's a huge vector, right? So these vectors, even though they appear really small in the rendering, there's just the relative sizes of vectors to the ones around them. But like, for instance, the vector at 416 is going to be huge, right? Because it's going to be negative 64 and 256. So these vectors up here are really, really large vectors. They don't look like it in this picture, because the picture is just showing the relative sizes of the vectors. Third of the class doesn't care. Okay. Any questions on this example? Okay, so what I want you to do is, I want you to first of all figure out what these two vector fields are. Again, from plus or minus x, plus or minus y, plus or minus 1, and 0. Those are your possible components. Plus or minus x, plus or minus y, plus or minus 1, or 0. Just figure out what these two vector fields are. Okay, Josh, did you get the one on the left? What do you think? You went negative 1y. Some people are nodding. Agree over here? Lots of nods. Sorry, it's wrong. It's negative 2y. Just kidding. But that, for your purposes, those are the same, right? I told you it had to be plus or minus 1. But so negative 2y is going to look basically the same as negative 1y. So good job. Good job. Got it. All right. How about the one on the right? Let's see. Adam, did you get this one? He wants negative 1x. No, x squared will be different. No, x squared is not on the table. So what is it? No, it's negative 4. Negative 2x. Okay, yeah. So negative 1x would have been the right answer to that question. Negative 1x. I just made it negative 2x for visual purposes. Okay, now what I want you to do is I want you to find. I want you to find paths, two paths. So I want you to parameterize two paths. The unit circle, one trip around the unit circle, okay, and then this path. Consisting of 3 segments. So like that, and like that, and then like that. So we'll call the unit circle will be C1. Okay, and then the triangle. Yeah, so this is 1. This is -1 here, and this is +1, and this is +1, and this is -1. Does that do it? And then the triangle will be C2. So I want you to, so the unit circle, you just have one vector function. The triangle will be, C2 will be made up of 3 vector functions. Okay, so this is called a piecewise continuous path, meaning it's all one path, but it's made up of pieces that are the end of one piece is the start of the next piece, and the end of the next piece is the start of the next piece, and then the end of that piece is the start of the next piece. So piecewise, that's what's called piecewise continuous. So C2 is a piecewise, it's a single path that's piecewise continuous. Does that make sense? So you'll need 3 vector functions for that one. So I want you to write the vector function for C1, and then the vector function for C2, which will be actually 3 pieces joined together. Yeah. It doesn't really matter in the end, but we'll start here. Okay, so we're just gonna find C1 and C2 now. Just develop the vector functions for those paths. C1, 1 trip around the unit circle, and C2, 1 trip around this triangle. Let's go this way, just because you asked. And then the unit circle will go counterclockwise around the unit circle. Okay, so you got a little work to do. You're either making progress or you're getting help. This was the goal here. So the circle should have been pretty easy. How do we parametrize the circle? Ezra, did you get that? Cosine t, sine t. Okay, let's see that. Unit circle, pretty easy. Okay, and then so now for these line segments, what I showed you was you could do the initial point. Like so for this diagonal line segment, you can take the initial point, which is -1, -1. It doesn't matter, right? So, well, I guess yeah. So then it just would be a matter of your bounds, right? So yeah. So if you make your initial point, if you make your initial point 1, 1. What? It doesn't matter. We're gonna do it. We're gonna go around the loop, so it doesn't matter where you start. So now, yeah. So with it, where do you want? Do you want the initial point here, A, exhibit A, or exhibit B? Doesn't matter, but where do you want it? So here. All right, we'll do the initial point here. Great. All right. So then that's -1, 1. So the way I showed you to do this was to do -1, -1, and then so that this would be t equals 0, and this would be t equals 1. So then you would look at, so at t equals 0, so we're going to have plus something t, right? Plus something t, plus something t. So when t reaches 1, I want x to be 1, right? So how much, so when I plug in t equals 1, I want the whole sum to be 1, so what should that be? 2, right? And what does 2 end up being then? What does that number 2 represent? Nope. Two has what to do with these x coordinates? The change, right? It's how much change there is from t equals 0 to t equals 1. So it's your starting x plus the change in x. So it would be the slope of the tx graph, but it's not the slope in this graph, okay? So if you were graphing x as a function of t, then yes, it would be the slope. But it's the amount of change that x goes through from the starting point to the ending point. So likewise, we'd have -1 plus how much change? So -1 for the y coordinate. How much change do we have for y? 2, and then we go check it out when t equals 1. Do we get the y coordinate of 1? Yeah, so that's one way to do it. So you can have your initial point plus the change in x times t, and then the initial y value plus the change in y times t. But if you have another way of setting up segments, of line segments, that's okay. But that's one way to do it. So there's the cosine t sine t, and then there's that, -1 plus 2t, -1 plus 2t. And then for the horizontal line, all we have to worry about is x, because what's the y coordinate going to be? So y is always 1. So that's just going to be 1. Let's just put a 1 there. And then now we do x. So where do you want starting x to be? Here. So starting x would be here. So then we'd start at x equals 1. And then what is our change in x? It's going to be 1 minus 2t. So it'd be 1 minus 2t, comma 1 would be this one. Likewise, going down here, your x coordinate is? Your x component, x component of this, -1. If we start here, our y will be 1 plus -2t, the change in y times t. So I think that's what I did here. So that's the diagonal segment. There's the left vertical segment, -1, 1 minus 2t, and then there's the top horizontal segment, 1 minus 2t and 1. Questions on parametrizing these paths? Yeah, William. If you do it this way, it doesn't have to be that way, right? So you could just write the equation of that line and do t and then the equation, but then you have different bounds. So the method that I'm showing you, yes, you're always making t go from 0 to 1, so the start to the end of the segment. Okay. So then we defined all these counterclockwise. Is that right? From here to here, and then here to here, and then here to here. But then I think we decided we're gonna go around this way. But that's okay. So then when we set up the integrals, we just have to get the bounds right. So for instance, when we set up this integral and go from here to here, t will go from what to what? No, 1 to 0, right? Because for this segment down here, this was t equals 0, the way we defined it, and this was t equals 1. So if we want to traverse the path this way, our lower bound will be 1, and our upper bound will be 0. That will take us from here to here. Does that make sense? All right, so now I want you to find 6 line integrals. You're going to do the circle for the left-hand field and the circle for the right-hand field. So they're going to do the circle for -2y and then the circle for -2x. And then you're going to do the triangle loop. We said clockwise, right? Clockwise triangle loop for the left-hand field and the clockwise triangle loop for the right-hand field. Is the task clear? 4 line integrals. The 2 paths in the left-hand vector field and the 2 paths in the right-hand vector field. And just as a matter of notation, because we're going around in a loop and we're ending up where we started, that's what this symbol means. So an integral with a circle like this. So you're doing C1 F1 dot dr1, and you're going to do also for C2, right? So it'd be So an integral with a little circle means that you're making a loop. You're making a loop, and you're ending up where you started. So you're going to do 4 of those. F1C1, F1C2, F1C1, or sorry, F2C1, F2C2. Go. You're either making progress or you're getting help. And remember the triangle, we're going to go clockwise around the triangle and counterclockwise around the circles, okay? And we'll make C1 be the circles. So maybe we can just set up the integrals. So hopefully you got to the place where you're setting up the integrals, and we can let my software do all the algebra. Maybe that'll help. So. Okay, so vector field number 1, path C1. For my integral, I got 2 sine t plus cosine t sine t. Is that right? And we're going from 0 to 2 pi, right? And you get 0. But this is 5.8 times 10 to the minus 16, right? So it's doing some kind of numerical method to find that integral, right? So it's ending up with a excruciatingly small number, okay, which is essentially 0, right? And you did the math purely by the algebra, it's truly equal to 0, okay? But by this whatever numerical method my software is using, they got this infinitesimal value, which indicates 0 for us. Okay, so now on the diagonal path, what does the integral turn out to be? So everyone can check. So along the diagonal, what does the integrand turn out to be in terms of t? Someone get it? Negative 2. So after you do the dot product, you get a function of t. Anyone have that?
4, negative 4.
Positive 4. Was it plus or times? So after you do the dot product, you just get it like a polynomial. So negative 4 plus, or 4 plus. Like that. Negative, so 4 minus 2 plus 4t. Clockwise, so it'll be from 1 to 0, because we define this as 1, right? We define 1 up here and 0 down here, so clockwise will mean go from 1 to 0, right? So then, so negative 4 minus 2 plus 4t? Yeah?
Yeah.
that something different? Mine, all negatives. Is that right? Okay, so what was it again? That segment right there was -1 plus 2t and -1 plus 2t. Okay, and then our dt would be 2. So we get -2 plus 4t minus 2 plus 4t. So minus 4 plus 8t. Is that what you got?
Wow.
Oh, yeah.
So it's -2 and then
My fault.
-1 plus 2t.
-2 and -1 plus 2t. Okay, so -4 and -2 plus 4t. Are we good on that? And then from 1 to 0, because that was defined from 0 to 1. So 1 to 0 will take us this way. Okay, cool. And then next one. Anyone get it? And anyone confidently have this integral up this left side vertical segment? Anyone confidently have that answer?
It's just
4. Just 4. Up the left side. From 1 to 0. Good. Okay, and then this one? This is now what? From left to right across that horizontal segment.
0. It's just going to be -2 plus 4t.
-2 plus 4t. You got that too? Okay, so this was, so again, the notation is this. So the red one. So this is like this. So we could say C1 F1 dot dr. And then this one, we could use this notation. All these three added together makes one loop integral around the path C2 F2 dr. What do you notice? They're both 0. Okay, how about the other way, the other side, so the other vector field? Have you worked on that one yet?
Yes. That one's
So let's just do the circle, and I'll lay the vector field to path C2 to U. But let's do the circle. So this is vector field number 2, path C1 will be from 0 to 2 pi. And now we have -2x. So will that be 2 sine t again? All right, but this time what? Cosine squared this time? And you should have gotten pi. Did you get pi when you did that one? How do you do the antiderivative of cosine squared? Do you remember from Calc 2? Did I mention it last week? something different? Is this correct? You all got loud to answer my question, not to correct this. It felt like you were correcting this. No? This is good? What's that? Yeah, half angle formula, right? Half angle formula?
Yeah, that's what we were talking about. It's negative 2 times negative sine.
Oh, yeah. Yeah, so in the cosine half angle formula, it's a positive, and the sine squared, for sine squared, the half angle formula is negative. Okay, yeah, so use the half angle formula. Okay, and so then did anyone happen to get all the way through the counterclockwise triangle path on the second one? Anyone make it all the way through? Oh, Chris, what'd you get? No, did you get all the way to the answer? It shouldn't be 0.
Should be a positive number.
Let's take a look at it. So we're going, how about along here? Positive or negative for this strip here? What would you guess? From here to here, would you think the line integral is positive or negative?
Tiny 0.
Positive. You got some positive contribution down here, right? Your components of these vectors are positive, and this is actually positive. It's actually positive the whole way, because they're all pointing a little bit forward, mostly left, but a little bit along the path. So positive. All right, and then what about along here? Negative the whole way, right? All these vectors are pointing against the direction, right? So all negative here, and then what about this? All strongly negative, right? So I would guess that if we do the clockwise loop here, we're going to get a negative value. We're going to get a negative value. So we have a little bit of positive here, but we got solid negative on the two horizontal and vertical paths. Okay, so what's going on here? This vector field, both loops gave us a 0 for the line integral. This one, both of them gave us a non-zero number. So why? What's going on here? So what is it about these two vector fields? What is it about this vector field or this vector field that's ending up resulting the way it is? So what about negative 2y and negative 2x? So what did we learn about some vector fields? Some vector fields are gradient fields. Is one of these a gradient field? How do we check it? So let's do it. Let's check it out. How do we check if it's a gradient field? Yeah, so if this is a gradient field, then negative 2 would be the partial derivative with respect to x. And then this would be the partial derivative with respect to y. These two pieces of information are two views on the same function. If there is this one function f that could possibly have those two as its partial derivatives, then we have a gradient field. So working towards that f function for this one, we would get negative 2x plus some function of y, so gy plus a constant. Okay? And then another view of that function f, same function f, but coming from the partial with respect to y, we could have some function of x, right, plus 1/2 y squared plus c. So can these two formulas resolve into the same formula? Or the same? Yes. And what would that formula be? Negative 2x plus y squared, 1/2 y squared plus c. Conclusion about field 1? It's a gradient field. And this is the potential function, right? The potential function is that, f of x, y. This is a gradient field, and that's the potential function. That's the multivariable function that has this field as its gradient, right? What is the gradient essentially? Relative to this potential function, the gradient is essentially what, in a word, what is it? Right, and so we can think of that as just simply the derivative, right? Because in any other direction, it's kind of like a fraction of that, right? So we can think of the maximum rate of change at any point as the rate of change. And then if we change the direction at that point, we would just be getting a fraction of that. Does that make sense? If you get some fraction, half of it, or negative 50% of it, or negative 1 of it, right? So this is, the gradient field is essentially the derivative of a multivariable function. So by finding the potential function, we're finding like the antiderivative of this derivative, right? So this is essentially the derivative, and that's the function from which it came. Okay, what about this one? So if you do the math, you'll find out not a gradient field. Because here you're going to have negative 2x, let's just do it fast, negative 2x plus some function of y. And then here, you could have some just function of x plus yx. Doesn't work because there's no yx up here. There's strictly minus 2x and strictly a function of y, but there's no term up here that's yx. So not a gradient field. So what we're seeing is a very important principle about gradient fields. And the important principle about gradient fields is that all closed loops are zero. And so this is the quality called, that gradient fields are called conservative. Gradient fields have this quality that they are conservative vector fields. Why? Because if you think about this as work, if you go around a path, what is the total work done to go all the way around the path? It's zero. So you have what? The conservation of energy, right? You have the conservation of energy in every closed loop in a conservative vector field. That's why it's called conservative, because the work that the field does in terms of positive is kind of like the energy that we put back into it when the work is negative, right? So it's some of the way around the loop. It's going to push. It's going to push on the particle and have positive work, but then some other places we'll be pushing against it. And so it's kind of like we're putting kind of energy back into the field. And so all the energy is conserved because we get back to the starting point. The total work is zero. The total work done by the field is zero. So gradient fields have this quality, which is called they are conservative. Okay? If it's not a gradient field, then they're not conservative. You will not have a conservation of energy. You go around the loop, and it'll be either a positive amount of work or a negative amount of work to get all the way around. And we saw that with both of the paths on this one over here. Yes, sir?
For gradient vector fields, will they just be a reflection on the other side? Is that
No. So there's all kinds of gradient fields that are that look different ways. There's really no hard and fast rule about symmetry. Yeah, Adam.
For a non-gradient field,
Yeah.
is it guaranteed to not be conservative, or is it just not guaranteed to be conservative?
If it's not a gradient field, it's not conservative. But that's not to say that you could have some loops that give you zero, but not all loops will be zero. So that in a conservative field, every closed loop through a conservative vector field will result in zero work. In a non-gradient field, you should be able to find one loop that's not zero, and then it's not a gradient field. Okay. The questions on that? Does that make sense? All right, so let's look more at this conservative vector field. And let's see another quality of the conservative vector field. So now I want to do so now I'm in the conservative vector field. What was it again? Negative 2y? I'm in negative 2y, and I've got this path here, which is now 3 cosine t, 3 sine t. And we will go, let's go clockwise from starting point to ending point. So let's set up, so what would the work, so will the work be 0, positive, or negative? What did you say? Yeah, everyone's saying negative. You should see that the work done from starting point to y isn't it 0? I'm not doing a loop, right? So I'm starting at one point here at 0, 3, and I'm ending at 3, 0. So let's set up so we're going to call this what happened. That happened. There we go. Okay. So this was, we'll call this C1. C1 will be clockwise from 0, 3 to 3, 0. And so then that would be the integral from, so set up that integral, okay? Set up that integral for that line integral for the work done from 0, 3 to 3, 0. Compare it with mine. Make sure I did it right. Did I do it right? Okay, and so let's actually find that value. So pi over 2, 2, 0 of 6 sine t plus 9 cosine t sine t. Negative 10.5, negative as we expected, right? Big important conclusion here. So now I want to go back along C2 here. And I want you to find the work to go from 3, 0 to 0, 3 along C2. What would the work be from 3, 0 to 0, 3 along C2? I'm done. Anybody else done? Who's done? Raise your hand if you're done. Tell me your name again. I forgot your name. Yeah. Will. What is it? From along C2 from 3, 0 to 0, 3? So what is it from 3? The question is find the work from 3, 0 to 0, 3 along C2. Charlie. Positive 10.5, right? Because we're in a conservative vector field and it would make a closed loop. So, how about this? Here's C3. Up there and over there. That's C3. Find the vector, find the work done from 3, 0 to 0, 3 along C3. Who's done? How much is it? Positive 10.5. Okay? How about this? C4. What's the work done to get from 3, 0 to 0, 3 along C4? 10.5. So this leads us to another quality of conservative vector fields. It's just called, so gradient fields are conservative. And conservative fields are what's called path independent. Meaning, given any fixed starting point and fixed ending point, the work done to get from that starting point to that ending point is the same amount of work regardless of the path. We just showed it, right? We just showed. To make this closed loop 0, we can go any way we want back from 3, 0 to starting from 3, 0 back to 0, 3. And we know that the total loop needs to be 0. Therefore, C2, C3, C4, they all give a work value of 10.5. And that's the idea of path independence. Given a fixed starting point and a fixed ending point, the work to get from A to B is the same amount of work regardless of what path you take. But you have to have a fixed starting point and ending point. If you have a different starting point and different ending point, it's going to be a different amount of work. So it's for a given start and ending point, the work or the line interval will be the same no matter what path you take. Okay, was there a question?
I was just thinking, in what real life application would you ever have like a conservative vector field?
I'm so glad you asked. You're living in one right now. Does anyone know? Gravity. Okay, so where's that? Hold on a second. This is really cool. Watch. No. Okay, I'll show you an example of gravity as a conservative vector field. So we'll start with that example on Thursday.